All right, so today we're going to continue with what we were doing yesterday. We're going over rational functions. Now, yesterday we went over the bare minimum. We just went over the function 1 over x, and we took a look at the graph, and we talked about, I know it's sideways over here, but we talked about asymptotes. So here's kind of a definition of an asymptote. It's an invisible line that a graph does not cross. Now, there are a few reasons for asymptotes, and there are different types of asymptotes. So that's what we're going to learn today. We're going to learn how to find them and their relation with the domain of our rational functions. So here we have some rational function f. Okay, so like we said yesterday, it's made up of two separate functions, a numerator function and a denominator function. All right, so here is just, a polynomial, right? So each of these are both polynomials, right? So nothing too fancy. And for now, we're going to say n of x and d of x have no common factors. So you can't, factor it like we were doing with our polynomial functions. So every rational function has two asymptotes. It has vertical asymptotes. And that we saw, it has vertical asymptotes at the zeros of your denominator. So whatever, wait, let me remind that. So yesterday we talked about we can't have 0 in the denominator. So when your denominator function is equal to 0, that poses a problem. That's, an error. So that's what an asymptote is. It's saying that this number can't be plugged into your function. Okay, so it's stopping the graph at that point, or at that line, x equals whatever. Then we also have horizontal asymptotes. So any rational function will have at most one horizontal asymptote. And the way we figure that out is by comparing the degrees of your numerator and denominator. So we're gonna be comparing the highest exponent in our numerator function and our denominator function. All right, so we have three different situations with our degrees of our numerator and denominator. So n is the degree of the numerator, okay, going back up, and m is the denominator. So if the numerator degree is less than the denominator degree, there's nothing involved. You just say that the graph has a horizontal asymptote at y equals 0. Okay, and that's what we saw yesterday, right? With our graph, let me bring it up. One over x, okay, the degree of 1 is 0. There's no x term. The degree of the bottom is 1, right? So here we have our vertical asymptote at x equals 0. So this blue line, my graph's not going to cross that, all right? No matter how far I go up, they may look like they intersect, but if you zoom in all the way, okay, they will never touch. It'll get closer and closer and closer and closer. You can see it's slowly getting closer, but they will never intersect. Same thing for our horizontal asymptote here. Okay, the line y equals 0. That green line, our function will never cross that green line. Our second situation, which we'll see an example of in a little bit, is when the degrees are equal. Then the graph has a horizontal asymptote at a ratio of your leading coefficients. All right. So again, not very much math involved. You're just looking at the two leading numbers, and whatever that may be, that is our horizontal asymptote. All right, so let me type in an equation where that might happen. Let me get rid of this. So this is kind of a funky one, all right? It doesn't look exactly like what we were looking at. But here I have 2x squared over 3x squared minus 1. So looking at my coefficients, I have 2 over 3. So if I graph the line y equals 2 over 3, well, there's my asymptote. My graph won't touch that line. Again, it gets really, really close, but it'll never touch. And then your final situation is something special that we won't get to probably till the end of our rational functions lessons, is when the numerator is greater than the denominator. Then the graph doesn't have a horizontal asymptote. It has what we call a slant asymptote. Okay, so just know that for now, and we'll take a look at that probably sometime next week. All right, are we good with all these notes? Take a look at some examples. All right, so we're going to find the vertical and horizontal asymptote. We'll start with the vertical. Usually those are the ones where you might have to do some work. All right, so we'll get that out of the way, and then we'll deal with the easy horizontal asymptote after. All right, so the way we're going to deal with the vertical asymptote is, well, we have to find the zeros of the denominator. So we're going to set our denominator equal to 0, and we're going to solve. Okay, so we have x squared minus 1 equals 0. So there's two ways you can do this. This is a perfect square where we can factor it, okay, or you can solve it using algebra. We're going to start factoring, though, because factoring does play a key part in rational functions in general. Okay, it'll help us kind of simplify things and make it easier for us. So x squared minus 1, we can change that to x plus 1 times x minus 1 equals 0. All right, so here we have two vertical asymptotes. X equals -1 and x equals +1. All right. Now your vertical asymptotes, I want to say this, is always going to be x equals something. Okay? They are vertical lines, right? Our vertical lines have the equation x equals a number. Right? That means x is equal to that number at all times. All right. And then in a second we'll graph this to show you. Now the horizontal asymptote Okay, we have to look at the degrees of our numerator and denominator. Here I have a degree of 2. Here I have a degree of 2. So I have n equals m. So going back, we're going to look at the leading coefficients. So my leading coefficient for the top function is 2. My leading coefficient down here, I don't see anything, but that's going to be a 1. So my horizontal asymptote is y equals 2. Again, horizontal is always going to be y equals. So what we can do real quick is we can rewrite this. Well, the top, that's going to stay 2x squared. I can't do anything to that. The bottom is going to be x plus 1, x minus 1. And what we want to do is we want to check to make sure that there are no common factors. Okay, and in this case, there's nothing up here that we can cross out with anything down there. Okay, so we got our 2 vertical asymptotes and our 1 horizontal. All right, so let me graph this and we'll take a look. So this is, we still got 2x squared, and I'm just changing this to x squared minus 1. All right, so here's our graph. Let me zoom out a little bit. So we had our horizontal asymptote at y equals 2. And there's that line where, so this one's a little different because we have squared, so you kind of have that parabola built in. We'll take a look at some others late in a minute. And then we had our 2 vertical asymptotes at x equals 1. There's that line there, that black line that this part of the graph won't cross, and then this part of the graph on the bottom won't cross. And we also have x equals -1. So this second line. So these straight lines, we don't see them when we actually graph them. Okay, they're, like we said, they're kind of invisible, right? But they're boundary lines that our graphs have to follow. Okay. Any questions so far? All right, let's take a look at another example. From here on out, I'm probably going to abbreviate. VA is vertical asymptote, HA is horizontal asymptote. It's a lot to write out, so I'm going to do that. All right, so now we're going to take a look at the function x squared plus x minus 2 over x squared minus x minus 6. So actually this time I'm going to start with the horizontal asymptote. Okay, again, we have the numerator and denominator are the same exponent. So our line is going to be at the y equals. Now, there's no coefficients there, so always remember that there are invisible ones. So 1 over 1 is just going to be 1. All right, so we got our horizontal asymptote. Our vertical asymptote. All right, so now remember we have to look at the denominator. X squared minus x minus 6 equals 0. So you can use the quadratic equation, right? The quadratic formula. But again, let's try to factor 2 numbers that multiply to 6 would be 3 and 2. They're negative, so one of them has to be positive, one of them has to be negative. They add up to -1. So we're going to make the 3 negative, since that's the larger number, and then the 2 positive. All right, so again, we have 2 vertical asymptotes. Let's look at the graph. No, I'll take that away for a second so you can finish copying as I type it in. So, like our last one, okay, we have 1 horizontal asymptote and 2 vertical asymptotes. All right, we had x equals 3 and x equals -2. But when we look at the graph, something's up. If I plot all my asymptotes, I get y equals 1 for the horizontal, and that looks like it matches up. That's fine, it doesn't cross. I have x equals 3. That was my 1. Okay, that matches up. But then I also have x equals -2. There we encounter a slight issue. Okay, here I have a horizontal asymptote, but my graph doesn't behave that like there is an asymptote there. It passes right through it. Now there's something special if we look at this graph. Let me remove this because we don't need it anymore. As I look at this graph, okay, if you had this on a physical graphing calculator, we have a hole in the graph. There, as you can see, the coordinates are -2, undefined. So what happens there? Well, let's take a look into our function, our original function. So we already know that our denominator can be broken up into x minus 3 times x plus 2. Now, our numerator, we can also break that up. We can also factor this out. All right. So we have, they multiply to -2 and they add to +1. Well, my only factors of 2 are 2 and 1. This one's going to be positive. That one's going to be negative. Here, our numerator and denominator have a common factor. So we remove them. So I can say that my function okay, we can reduce that to just x minus 1 over x minus 3. This here, we have a special name for this. And we call that a removable discontinuity. All right, so that is a special feature of our rational functions. There are certain times I know, because of my denominator here, right? If I was talking about the domain, we have that x can't equal 3 and x can't equal -2. So those are rules that are true because my original function, the denominator, we can't have 0 in the denominator, right? You plug in 3, you get 0. You plug in -2, you get 0. But what happens is when we simplify things, that restriction isn't there anymore. Okay, down here in this simplified version, I don't have the restriction that x can't equal 2. So here you would say x can't equal 2, or I'm sorry, negative 2, because it's a removable discontinuity. Now let's graph this, x minus 1 over x minus 3. What? Why is it giving me that? Oh, x equals now. Well, look at that. They are, if I turn them on and off, if I can turn them on and off, they're the same function. Okay, but this green function, if I turn the red one off, it doesn't have that restriction at negative 2. Okay, I can plug in negative 2 and I can get 0.6. But here, okay, it looks that way, but if you graphed it, you would have a hole at that graph because we call it a removable discontinuity. All right, any questions?
No.
Okay, so I know you guys have the larger assignment that's due Monday. I'm gonna put up a few multiple choice questions based on this tonight. Just asking about, what is the horizontal asymptote, things like that. Excuse me. Tomorrow we'll continue with actually graphing them, and I'm going to take a look, and we have some of those GeoGebra practice things, so we can do some interactive things with this as well. All right, guys, so keep up the work. All right, make sure you finish that one assignment that's due Monday. The sooner the better. And yeah, that's it. All right, guys, no other questions?